Assalamualaikum everyone. In today's video we are gonna learn about rectangular waveguide, and for that we need to start from the basic of rectangular waveguide. So what is rectangular waveguide? Rectangular waveguide is basically a hollow metallic tube. You can see in this picture it's a hollow metallic tube, and as the front is rectangular, that's why we say it a rectangular waveguide. So why do we use this rectangular waveguide? Basically we use to transmit the EM wave. Whatever we are reading in this chapter related to the EM waves, so it's used to transmit the EM wave. And rectangular waveguide has less attenuation loss compared to the transmission line. That's why we use it more than the transmission line. And another important thing is, like, rectangular waveguide allows only TE and TM modes, transverse electric and transverse magnetic. It doesn't allow the TEM mode. And the dominant mode for this rectangular waveguide is TE on 0, which means 1 0. That means M is equal to 1 and N is equal to 0. You can see the diagram for the rectangular waveguide here: x-axis, y-axis and z-axis the hollow tube, and the frontal is rectangular. Here it's A and it's B. Now we will learn about the cutoff frequency and wavelength of the rectangular waveguide. So the cutoff frequency fc is equal to c by 2 to square root of m by a whole square plus n by b whole square. So fc, here c means the cutoff frequency, and c by 2 velocity of light c divided by 2, and m and n, we know what's m, and a and b. A is the length towards the y and b is towards x, and it's the cutoff frequency. And then the cutoff wavelength is 2ab divided by root over m square b square plus n square a square. So in the previous page we talked about the dominant modes of the dominant mode is TE10. So in TE10 we gonna input m is equal to 1 and n is equal to 0, and we find the dominant modes for the cutoff frequency is c divided by 2a, putting n is equal to 1, n is equal to 0, and the wavelength of the dominant mode is 2a. Similarly, putting n is equal to 0 and m is equal to 1. So this is how we find the cutoff frequency and wavelength using these two equations, and the dominant modes for the rectangular waveguides. Now we are going to cover the intrinsic wave impedance. First of all, we will learn the intrinsic wave impedance of the TE mode, transverse electric mode. So we denote the wave impedance as eta, and eta TE means eta transverse electric mode is equals to 120 pi divided by 1 minus root over fc by f whole square. Here we can write fc by f is equal to sine theta. And what is theta? Theta is the tilt angle. So if it's a parallel plate and the signal is passing through this line and reflecting this, so to the wall the signal is reflecting, or the wavelength is reflecting. The parallel angle, the tilt angle is theta. And as these two lines are parallel, we can also say this is the theta. This angle and this angle are the same, so it's the theta, and fc divided by f is equal to sine theta. So what it stands, eta t is equal to 120 divided by 1 minus sine square theta, and 1 minus sine square theta means cos square theta, and the square root of cos square theta is cos theta. So finally we can write that eta te is equals to 120 divided by cos theta. It's the simplified version, simplified equation of TE mode of intrinsic wave impedance. And then we will learn about the TM mode of intrinsic wave impedance, that means transverse magnetic mode. So what is it? The equation is T eta Tm is equal to 120 pi into root over 1 minus fc divided by f whole square. So similarly, fc divided by f means sine theta, 1 minus sine square theta. Theta is the tilt angle as we said before, and 1 minus sine square theta means cos square theta, and square root of cos square theta is cos theta. So eta tm is equals to 120 pi into cos theta. So basic difference is the cos theta is divided by here in the denominator, and here is multiplied. And TEM mode is not possible, as we learned before that TEM mode is not applicable for the rectangular waveguide. So intrinsic wave impedance will not be will not be appropriate for TEM mode. Now the final topic we are gonna cover about this topic, rectangular waveguide, is phase velocity and group velocity. Phase velocity is denoted by Vp and group velocity is denoted by Vz. The V comes from the velocity, and as it's our phase velocity, so here we will write V of P. V of P is equals to C divided by root over 1 minus Fc divided by F whole square. Similarly, we learned here 120 pi divided by root over 1 minus Fc by F whole square, and here the difference is C divided by. So we can replace this. We have written it as with respect to the frequency, but we can also write it with respect to the wavelength. So if we convert the phase velocity from frequency to wavelength, so we want to write c divided by root over 1 minus lambda naught divided by lambda c whole square. Here when it's the matter of frequency, we have retained cutoff frequency divided by operating frequency, but when we gonna write about the wavelength, with respect to the wavelength, we wanna write the operating wavelength divided by cutoff wavelength. And similarly, for group velocity Vz, C will be multiplied as before we have seen. Here the intrinsic wavelength we had 120 pi, and for velocity we are having C, because it's the velocity of light. And so here we can write Vg is equal to C into square root of 1 minus Fc divided by F whole square. Similarly, C into root over 1 minus lambda naught divided by lambda c whole square. So what's the relation between the phase velocity and the group velocity? If we multiply the phase velocity and the group velocity, we will have c square. See, we are multiplying this and this equation, c into c square, and 1 minus fc by f whole square, and 1 minus fc by f whole square will be eliminated, so we will have only c square. So here we conclude the discussions about the rectangular waveguide. Assalamu alaikum warahmatullahi wabarakatuh.